All right, so this is the first of several parts looking at using what we've seen about functions in the last lessons and applying them and using them as models. And the focus today is a variety of things. First of which is just reminding how we can solve essentially any equation by graphing. So I have an equation here that's quite complex in itself, and there's always basically two approaches of solving by graphing. One is to graph the left and the right-hand side separately. So one of your equations you would graph is y equals x to the power 4 plus 2. Another equation you would solve is y equals 10 minus 2e to the negative 1/2 x. And graph these two equations and see where they intersect. And in general, that's what I would recommend. And in any graphing device, it should be fairly quick. Just keep in mind, you want to make sure you adjust your window settings enough so you can make sure you're seeing all the solutions. And if I solve it like this, here's my two functions. I realize there's only two solutions, and those two solutions I can see are here. And so to three significant figures, one of my solutions is negative 1.41, and my other solution is positive 1.63. It's the x values of where they intersect. And so I'll write that down, and then I'll mention quickly another approach that's no better, it's no worse. And so either way, one of my solutions again, x is approximately negative 1.41 and approximately 1.63. So while it is done, another approach, if you don't want to graph two equations, is to graph just a single equation by bringing everything over to one side, essentially making your equation equal 0. So in this case, I could choose to, for example, subtract 10 from both sides and add 2e to the negative 1/2 x to both sides. And in doing so, I get an equation that equals 0. And if I do that, I can find my solutions by, let me show you. So what I have here is the graph of what I just described. It's the graph of, the left-hand side and the right-hand side, should I bring it over. Because if I'm looking at this as a single equation, then I'm trying to find where this equation equals 0, which is the equivalent of the zeros or the roots or the solution of the equation, which are the x-intercepts, which notice I get the same values. In general, this is a bit more work, but it's not much work, and either way, it's quite quick, and I can solve this quite nicely. All right, so next, let's look at this quadratic function here. I have a quadratic function because I tell you it's a quadratic function, and you can see 3 points it goes through. Just from those points, we want to find the equation of the quadratic function. Now, if I just look at these 3 points, first, while it's not essential, it is helpful to try to visualize what it must look like. For example, I know it can't look like this because that's not what parabolas look like. And while, again, it's deceivingly tricky, I do have a sense it has to look something. The vertex has to be down here, and it has to look something like this. Just because I'm familiar with what parabolas look like. However, that in itself doesn't really help me much. It just gives me a bit more of a visual. But what does help me are these 3 points. So 1, 0, 2, 9, and negative 2, negative 3. There's only one way a parabola can go through these 3 points. And how to solve it is, let's look at these 3 equations. For example, the point 1, 0, that means I know when x equals 1, y equals 0. So in my general quadratic expression, I know that when, if I have ax squared, if I have a times 1 squared, when x is 1, plus b times just x, so 1, plus c, I know this must equal the y value, the output, which I know must be 0. And so I know this equation must be true. Cleaning it up slightly, really, all I have is a plus b plus c must equal 0. So in itself, that doesn't do me any good, but I can do the same thing for my other points. When x is 2, y must equal 9, which means a times 2 squared plus b times 2 plus c must equal 9. Or cleaning this up slightly, I get 4a plus 2b plus c must equal 9. And if I do this one more time for my last point, negative 2, negative 3, I know when I have a times negative 2 squared plus b times negative 2 plus c, all of that must equal negative 3. Or cleaning it up, 4a minus 2b plus c must equal negative 3. And now what I have are three equations with three unknowns, three linear equations, 1, 2, 3, and we've seen before how we can use our simultaneous equation solver on any of your graphing devices to solve this. And so I'm going to graph these three equations right here. And sorry, I'm not going to graph them. I'm going to solve them using the simultaneous equation solver, which we've seen from previous lessons. And instead of A, B, and C, I'll have X, Y, and Z. And you should fairly quickly get to these values. So using your GDC, I should get to my A value, or actually be X on my graphing calculator. But A equals 2, B equals 3, and C equals -5, which means my equation for f of x must be f of x equals 2x squared plus 3x minus 5. And since I have a graphing device, I would highly recommend we just check and see if this is correct. So if I go back to Desmos here, if I turn this off, here are the points that we were given, and here's the equation I just figured out, and it works. And so keep in mind, if I go back, if you were to try to solve this system, because I have a 3-variable system here, if you were to try to solve this without your GDC, it is doable, but it is so much more work, and it really should be, once we have a strategy, it should be really quite quick. All right, lastly, I have data here on the average carbon dioxide levels in the atmosphere from 1980 to 2016. And so one thing I want to do is create a scatter plot on my GDC, and then create a linear model by looking at the first and last points. So first, let me make my scatter plot here. And it's not essential to have to make this part, but I'll kind of show it here. Now, I have my scatter plot put into Desmos here, and I'm just leaving the years as the x-axis and the carbon on the y-axis. And so for this, I want to check. I'll just kind of adjust my scales here. Oh, there we go. There we go. All right, so that's showing my scatter plot. You can see it has a linear model, seems to make sense here. So how do I come up with a linear model? So there's two approaches we eventually want to do. First, we're asked to create a linear model by looking at the first and last data points. So keep in mind, any linear equation can be written in this form, point slope form or gradient slope form. And this tends to be quite helpful anytime we know a point, and we know many points, and we can find the slope. And the idea is, okay, well, let's use the first and last points to find my slope. And so in this case, my slope or my gradient will be the change in y. So in this case, from 401.7 minus 337.5 divided by the change in x, which in this case is 2016 minus 1980. And if you do that, you should get actually exactly 1.783 repeating. So there's my gradient, which represents every year, on average, the carbon dioxide level in the atmosphere in parts per million is increasing just shy of 2 per year. And now for the other part of my equation, I just need a point. I got many points. I'm going to use 1980 and 337.1. So I'll think of 1980 as being my x1, this is being my y1. And so my equation becomes this: y minus 337.5 equals 1.783. Repeating, I'll be as exact as possible. X minus 1980. Now I could clean this up. All I'm going to do is add 337.5 to both sides. I'm not going to distribute anything over here. So I get my equation being this: y equals 1.783 repeating plus 337.5. All right, and so keep in mind for this equation, which if I want, I could distribute this, but there's no real benefit to that. I now want to use this to determine the CO2 levels in the year 2030, which in this case, I just replace X with 2030. And if you do that, you should get y equaling, because I can just figure that out quickly on a calculator, I should get about 427 parts per million. Now, before I go on, maybe what I'll do is look at this visually, and I want to see how accurate on my graphing device my linear model appears to be. So let me go back to Desmos. And this is the scatter plot. And here's the equation I came up with, which seems quite good. Let me adjust my scale here slightly so I can zoom in more. Let's see, that's a bit better. So notice a pretty good model. It goes through the first and last points, of course, because that's how I set up my model. So it seems to be a pretty accurate model. This last part of the question is, we can also come up with a model using regression, and we've done that earlier. So I want to come up with a least, when it says a linear regression model, we did that a lot with our earlier in the course. And so since you probably already have a table in your GDC, you can just use a linear regression. And if you do that, you should get a different looking equation. I get y equals approximately 1.76x minus 3,153.34. And when I graph it, though, you'll notice it is extremely similar. So this is what I just figured out. And they are different. If I zoom in, you can see they are different. And in many ways, the regression model is probably a little bit better because it uses all the points of data, not just the first and the last. But it's a pretty similar model to what we had before. And the correlation coefficient is almost 1. It's 0.9974. So it is an incredibly strong correlation coefficient here. So I'll write that R is approximately 0.9974. So the comment on the statistical significance, we have a very strong correlation. And so I still can't comment too much about the accuracy of the 2030 because we are extrapolating. But it's, considering we have such a strong correlation here, it definitely seems to be a pretty reasonable prediction, even though we are predicting a solid 14 years following the data. So we are extrapolating a fair amount, but definitely for staying close to the data, I think we can use any of these models quite accurately. These two models are extremely close to one another, which again, graphically is quite apparent there.